When you think about the most powerful forces on our planet, what comes to mind? Volcanoes, earthquakes? Well, what about silent, slow-moving rivers of ice? Today, we're diving into the world of glaciers, these incredible architects that have literally sculpted our world, carving out massive valleys and shaping entire continents. And it all kicks off with one simple question.
I mean, it sounds kind of crazy, right? How can something as delicate as a snowflake, over time, become a force that can grind down entire mountain ranges? That's the big mystery we're going to unravel today. And believe me, the journey is going to take us from a single flake of snow to continents completely encased in ice.
So here's our game plan. First, we'll start at the very beginning, how a glacier is even born. Then, we'll get to know the two major types of these ice giants. From there, we'll zoom way out to see how they took over the planet during the Great Ice Ages. And finally, we're going to become detectives and learn how to read the clues they left behind, etched into the very rock beneath our feet.
All right, first things first. Where do these colossal things even come from? It all starts with a really simple process of piling up and squishing down, turning something as fragile as snow into this relentless natural force.
You know, this whole transformation takes centuries. First, you just need a place where more snow falls in the winter than melts in the summer. Simple enough. But as decades of that snow pile up, the weight becomes absolutely immense. It compacts the layers below, squeezing out every last pocket of air. And that incredible pressure forges the snow into something totally new, this dense, blue, crystalline glacial ice. Once that mass gets heavy enough, gravity takes over and the whole thing starts to move.
Now, it's important to know that not all glaciers are the same. They pretty much fall into two main categories, and what separates them is where they are and, more importantly, how they move.
On one hand, you've got your alpine glaciers. You can think of these as true rivers of ice. They're born in the mountains, they're stuck in valleys, and their flow is all about going downhill. But on the other hand, you have the titans, continental glaciers. We're talking about the massive ice sheets that are burying Antarctica and Greenland. These things are so huge, they basically create their own weather and their own movement. They don't need a slope, they just flow outward under their own colossal weight.
Here's a great way to picture it. Imagine pouring sand onto a table. As the pile gets bigger, the sand doesn't just stack up, right? It spreads out from the middle. Well, a continental glacier works exactly the same way. It flows from its thickest, heaviest center towards its thinner edges, all driven by its own incredible mass.
Now those alpine glaciers, they kind of operate like a bank account. Up at the top, you have the zone of accumulation. That's where it's earning ice, with more snow piling up than melting. Down at the bottom, you have the zone of ablation, where it's spending ice, because more is melting away. And that line in the middle, the equilibrium line, that's the break-even point. It tells you if the glacier is growing or if it's shrinking. So what happens when thousands of these glaciers all over the world have their budgets in the black for centuries? Well, you get an ice age. These are periods when glaciers just grew and grew until they covered huge chunks of the planet.
So what is an ice age, really? It's not just a super long cold winter. We're talking about a whole chapter in Earth's history, lasting for millions of years, where somebody turned the global thermostat way, way down. This is what allows those huge continental ice sheets to spread out and just bury entire continents under kilometers of ice.
And this wasn't some one-time thing. Oh no. Earth has been through at least 5 major ice ages. And just look at this timeline. We're talking about events that happened billions of years ago, like the one they call Snowball Earth, all the way up to the ice age that we're technically still in right now, the Quaternary glaciation.
You know, there's a really interesting rhythm to how these ice ages work. They creep in super slowly, with the planet cooling over tens of thousands of years. But when they end, it's fast and it's dramatic. It's kind of like the difference between fall and spring. The cold just slowly settles in, but the thaw feels like it happens almost overnight.
Okay, so even inside a single ice age, the climate isn't just stuck on frozen. It actually pulses back and forth between these long, deep freezes and much shorter, warmer thaws. These are the two key phases we need to get our heads around.
These phases are called glacial and interglacial periods. During a glacial period, it's cold. The ice sheets advance and they lock up so much water that sea levels can drop by 100 meters. But during an interglacial period, which, by the way, is what we're in right now, it's warmer. The ice sheets pull back and all that meltwater makes the sea levels rise again.
And here's the kicker. This is the part that just blows my mind.
Within an ice age, the planet's default setting is cold. These long frozen glacial periods last 7 to 9 times longer than the warm spells. Think about that. Our current warm phase, the one that all of human civilization has happened in, is just a short little warm break in a much, much longer, colder cycle.
So, how in the world do we know any of this? Well, it's because glaciers, for all their power, leave behind a ton of clues. Geologists basically act like detectives, reading the scars that these ice giants carved and dumped all over the landscape.
One of the biggest clues is something called glacial till. The best way to think about it is to imagine the glacier is a massive, messy conveyor belt. As it grinds along, it just scrapes up everything in its path, huge boulders, sand, fine clay, and mixes it all up. Then, when the ice melts, it just drops the entire messy load in one spot. What you get is this chaotic jumble of rock that is the absolute, unmistakable footprint of a glacier.
That grinding power also pulverizes rock into a powder that's as fine as flour. They call it glacial flour, and it's so light that it just hangs suspended in the meltwater. This, right here, is the secret behind those stunning, milky turquoise mountain lakes. You're not just looking at water, you're seeing sunlight bouncing off billions of tiny particles of a ground-up mountain. And then you've got these. Glacial striations. Picture giant rocks trapped at the bottom of the ice, acting like the teeth of a massive file. As that glacier scrapes across the land, those teeth carve deep scratches and grooves right into solid bedrock. They leave behind a permanent record, like fossilized tracks, showing not only the glacier's power, but the exact direction it was moving. And this is where the real detective work kicks in. In places like Mount Rainier or out in Nova Scotia, geologists find these crisscrossing sets of scratches. By figuring out which grooves are on top of other ones, they can piece together the whole complex history of ancient ice flows, mapping how different glaciers moved across the same spot over thousands of years. It's incredible. So this all brings us to one final, kind of humbling thought. We've learned how to read the story that ancient ice wrote on our planet, but now we're the ones carving our own story into the rock. It makes you wonder, right? Thousands of years from now, when the geologists of the future are digging through our layer of history, what clues will they find? What story will the Earth tell about us?